Good morning, students. Today we continue with the previous year problems for the solutions for the problems. So this year, that is in March. So this year they asked the problem based on the prism. So here the question is, at what angle? At what angle should a ray of light be incident on the face of an on the face of an equilateral prism so that it just suffers total internal reflection at the other face at the other face the refractive index of the refractive index of the material of the prism is 1.5. So here the given one prism. So here we have to find out at what angle should a ray of light, that is incident angle. We have to find the incident angle of the equilateral prism so that it suffers total internal reflection at the other face. So if we draw one prism like this, so this one is the prism and here is the base of the prism, right? So the light enters at the first phase. So this one is the incident ray. If I draw the normal, so this is the angle of incidence. We have to find out this angle of incidence when after incidence on the first phase, the light refracted into the medium and this acts as the incident ray for the second phase. In the question, they told that this incident ray just suffers the total internal reflection at this second surface. Then the refracted ray will go like this. So if we draw the normal here, the angle of emergence is 90 degree because it just grazes the second surface. So here this is the I1, then here this one is the angle of refraction R1, and here for the total internal reflection, so this angle we taken as critical angle IC, or R2 is equals to IC, and the angle of emergence is equals to 90 degrees. So the given the equilateral prism. So the prism angle is equilateral, means all the angles are equal. Then sum of the angles is 190 degree for the triangle. Then angle of the prism A is equals to 60 degree. And also they given the refractive index of the prism N is equals to 1.5. So this one is the refractive index of the prism. So next we know the relation between the refractive index and to the critical angle. That is, we know that n is equals to 1 divided by Sine IC. That is sine IC is equals to 1 divided by n. We know the value of n. So 1.5 can be written as 3 divided by 2. Ones are 2, remaining is 1.10, that becomes 1.5. So in place of n we can write 3 by 2, that is 1 divided by 3 by 2. So it becomes sin c is equals to 2 divided by 3. Sin IC or sin C. This is the critical angle. So 2 divided by 3 is, so if you put 1 point then it becomes 20. So 3, 6 are 18 like that. So it becomes 0.667. So we need the critical angle IC, then IC is equals to sine inverse of 0.667. From the sine table, we can find the value of sine inverse 0.667, that is equals to 41 degree. That is equals to 41 degree. So from the relation between the refractive index and to the critical angle, we find the angle of, that is critical angle is equals to 41 degree. So we know, so this is the angle of the prism. So while doing the derivation, we get the relation R1 plus R2, that is equals to angle of the prism. So here we don't know the value of R1, then R1 plus in place of R2 we have IC, that is IC. R1 plus IC, that is equals to A. Here it is IC, that is equals to A. That is we taken R2 as IC. So here we know the value of IC and also we know the value of A. Then we get the value of R1. R1 plus the value of IC, here we get is 41 degree. That is 41 degree. That is equals to, if the given equilateral triangle, that is angle A is 60 degree, then R1 is equals to 60. If we shift that one 41 to the RHS, it becomes minus 41. Then the value of R1 is equals to 95 minus 24. That is R1 is equals to 19 degree. Now applying Snell's law, for the first phase, applying Snell's law for the first phase, then we have the refractive index N is equals to sine I divided by sine R. Here it is R1. Sine I divided by sine R1. So next we want the value of I, then sine I is equals to N into sine R1. The value of N, that is 3 divided by 2, that is 1.5. 3 divided by 2 into sine of the value of R1 we calculated here is 90 degree. So from the sine table, if we calculate the value for sine 90, we have that value is 0.3255. That is 3 divided by 2 into 0.3225. So this is the value of the sine. This value we find out by using the sine table. So if we simplify this one, we get, so 0.3 into 3, that is 0.9 divided by 2, that is approximately is equals to 0.4. We get 0.488, that is sine I. Sine I is equals to 0.488. So we need the value of I, then I is equals to sine inverse of 0.488, then its angle is approximately equals to 90 degree. So this one also we find out by using the timetable. So the final angle of incidence I, that is 29 degrees. So this one is the final answer. That is, we need to calculate the angle of incidence I. First, we have to calculate the angle of incident on the second phase, that is critical angle, because here the total internal reflection takes place. That's why we are taking the critical angle. So we know the formula, the relation between critical angle and the refractive index, n is equals to 1 divided by sin c or sin ic. From this relation we calculate the value of critical angle, that one is 41 degree. From the derivation we know r1 plus r2 is equals to a, that is sum of the angle of refraction is equals to angle of the prism. Here we find out the angle of refraction for the first phase, then by applying the Snell's law we calculated the value of I. So this question is asked for 5 marks this year, right? So next question. So if we practice the derivation properly, then only we can find the proper values and using the proper formulas to solve the problem. So the next question, they are asking July 2018. They ask this question, that is the radii of curvature, the radii of curvature of two surfaces of convex lens is 0.2 and it is 0.2 meter and 0.22 meter. Find the focal length of the lens. Find the focal length of the lens if refractive index of material, if refractive index of the material of lens is 1.5. Also find change in focal length, if it is immersed in water of refractive index, immersed in water of refractive index 1.33. So this question is asked in July 2018. So here the radii of curvature of two surfaces of the convex lens. They given one convex lens. So this one is the convex lens. So it has two surfaces. Then the lens has two radius of curvature, that is R1 and R2. They given R1, the radius of curvature given R1 radius of curvature is 0.2 meter and radius of curvature R2 is equals to 0.22 meter. Next, find the focal length of the lens if the refractive index of the material of the lens is 1.5, and also they given the refractive index of the material is 1.5. For this condition, we have to calculate the focal length, right? The question is further extended. Also find the change, that is change in focal length when if it is immersed in water of refractive index 1.33. That is the same convex lens is immersed into the water. Then we have to find the focal length of the convex lens. That is focal length of water. Focal the lens in water. For that, they given the refractive index of water, that is equals to 1.33, and also that is to find the change in focal length. To find the change in focal length, we need to find the focal length of the convex lens in water, that is delta F, that is change in focal length, that is equals to focal length in water to the focal length of the lens in air. If they didn't give means that one is in air medium. So we need to find out these three. Right? So we know the lens makers formula by using lens makers formula. So the lens makers formulas 1 by F, that is equals to N minus 1, that is N to 1 refractive index of second medium with respect to first medium. If the lens is glass medium, if this one is the glass, that is N, then it becomes NGA, that is glass medium to the air medium, that is for the first case, minus 1 divided by 1 divided by R1 minus 1 divided by R2. For convex lens, the radius of curvature R1 is positive and the radius of curvature for convex lens R2, that is negative. R2 is negative and R1 is positive. This is for the from the sign convention. So here we know all these values, we can easily calculate the focal length, that is 1 by F, that is equals to 1 by F, that is equals to Ng divided by Na minus 1, that is 1 divided by R1 minus of 1 divided by minus R2 from the sign convention. So we know the values. Refractive index of glass medium, that is 1.5, refractive index of air medium, that is 1 minus 1 into 1 divided by R1, that is 1 divided by R1 is plus, that is 1 divided by 0.2, minus into minus, it becomes plus 1 divided by 0.22. So 1 divided 1.5 by 1, that is 1.5. 1.5 minus 1 is, that is equals to 0.5 into, if we take LCM here, then we get 0.22 plus 0.2 whole divided by 0.2 into 0.22. So we need F value. If it goes to numerator F, that is equals to 0.2 into 0.22. 0.22 plus 0.2, that is 0.42 into, here it is 0.5. So if we simplify this one, then we get the focal length of the convex lens is 0.21 centimeter, right? So if we simplify by using calci or by direct, we get the values. F is equals to 0.21 centimeter. So this one is the focal length of the convex lens in the given medium. So we calculated F. Next, we move on to find the change in focal length. That is when the lens is immersed in water. This is first equation, that is in air medium. If the same lens is placed in water medium, so here is refractive index of water and here is the refractive index of the glass. Then if we write the formula for, if we write the formula, lens maker's formula for focal length of the glass, that is convex lens in water medium, 1 divided by Fw, that is equals to N GW minus 1 into 1 divided by R1 minus 1 divided by R2. Right, this is the second equation. So if we observe, the value of 1 divided by R1 minus 1 divided by R2 is same, that is constant for the given convex lens. Then divide equation 2 by 1. Divide equation 2 by equation 1. Right? So dividing this equation by this equation, then in the numerator it becomes 1 divided by Fw in the LHS divided by 1 divided by F, that is equals to N GW minus 1 into 1 by R1 minus 1 by R2 whole divided by A minus 1, that is 1 divided by R1 minus 1 divided by R2. So in the numerator, denominator, the radius of curvature of the lens is constant, then we can cancel. So it shifts to the numerator, then F divided by Fw, that is equals to, so NGW can be written as Ng divided by Nw minus 1 whole divided by Ng divided by Na minus 1. We need to find the focal length of lens in water, that is Fw. So Fw, that is equals to F into Ng by Na minus 1 whole divided by Ng divided by Nw minus 1. Now we substitute the values. We know the refractive index and also focal length of the convex lens in air medium. Then if we substitute the values, Fw is equals to, here the focal length we get is 0.21 into refractive index of glass is 1.5 divided by 1.33 minus 1 whole divided by the refractive index of glass is 1.3 divided by 1 minus 1. So if we simplify further, so Fw is equals to, that is 0.21 into 1.5 minus 0.33 whole divided by the denominator term is 1.33. If we take LCM here, 1.5 minus 1.33 whole divided by 1.33, that goes to the denominator, means we get 1.33. So here, so this one is glass, that is 1.5. 1.5 divided by 1 is 1.5 minus 1, that is we can write 0.5 into 1.33. So if we simplify, we get the value Fw, that is equals to 0.82 centimeter. So this is the focal length of the convex lens when immersed in water. So here we have to find the change in length. For the change in focal length, that is f delta f is equals to fw minus f. That is focal length when the lens is in water. That is the focal length when the lens in the air medium. So the value of fw is 0.82 minus the value of f is 0.21. So that is equals to 1 8 minus 2, that is 6, 0.61 centimeter. That is change in focal length. So this is the solution for the given question. So this one is the final solution, right? So by using the lens maker formula, we can find out the focal length of the convex lens in any medium. Here they given two medium. First the lens is in the air medium, then we have to calculate the focal length of the lens. Then the same lens is placed inside the water, then we have to calculate the focal length of that lens in water medium. So this one is for 5 marks. So from this chapter, once they ask the question for 1 marks, that is for one problem for 1 marks, that is on the topic power of the focal length, that is power of the lens. They ask the question on the power of lens. They given two lenses of power. They given P1 is equals to plus 5 diopter and P2 is equals to minus 3 diopter. Then find the net power of the lens. Net power of the lens in contact. That is, we know the formula P is equals to P1 plus P2. They given P1 plus 5 plus of P2 is minus 3, then it becomes 2 diopter. So like this question they ask for 1 marks, that is power. If they didn't give power directly, if they given the focal length f is equals to 10 centimeter of lens and focal length of the another lens, then we have to change the focal length into power. That is, we have to convert the focal length in terms of power, and then finally we have to calculate the power. We know the relation P is equals to 1 divided by F, right? So power is always in diopter, that is per meter. Then 10 into centi is 10 to the power of minus 2 meter, and 5 into 10 to the power of minus 2 meter. Then 1 divided by 10 into 10 to the power of minus 2, that is 10 to the power of minus 3 diopter. Next, here it is P2. In the same way, 1 divided by 5 into 10 to the power of minus 2, that is 0.2 into, sorry, it goes to numerator, then it becomes plus 3. Here it is plus 2, that is 20 into 10 to the power of 3 diopter. If we calculate the net power, P is equals to P1 plus P2. That is, here it is 1 into 10 to the power of 3 plus 20 into 10 to the power of 3, then it becomes 20 into 10 to the power of 3 diopter, like this. Okay. And next, For 1 marks, they ask the image formation. That is, if the object is placed beyond the center of curvature, then what about the magnification? So what is the magnification of that object? And they may ask where will the image is formed. That is image formation. We have to know that one. Image formation in concave mirror. To form the images of an object, we have to take minimum 2 rays, then we have to trace that one path, and at point of meeting we get the image of that object. So directly, so this one is the concave mirror and this one is the principal axis. So here we have one point, that is focus point, and the second point is the center of curvature, right? So here in the first case, when the object is at infinity, right? In the first case, that is case 1, when object is at infinity. When object is at infinity, then the image is always formed at the focus, because the rays which are coming from infinite distance, after falling onto the concave mirror and it gets converges at the point, that point is the focus point. So if the object is at infinity, then we get the image at the focus, right? So this image is, so if you take this one as 1, or it is A. So here I am taking in the first case as A. A dash is the image of the object which is placed at infinity. So if you observe here, the object is above the principal axis, then we get the image is inverted. So here the image formed by the concave mirror when the object is at infinity means the image is formed at the focus and it is inverted and it is small in size, right? So hence we know the magnification m, that is equals to, we know the formula magnification m is equals to minus b divided by u, that is image distance to the object distance. So here the object distance, if you take in terms of height, magnification is equals to height of the image to the height of the object. So here height of the image is very less and magnification, the height of image is inverted. If we take convention, then height of the image is negative, right? So height of the image is less than height of the object, then magnification is very less than minus 1, right? So this is the magnification for the object which is placed at infinity. We get the image at the focus and its magnification is very less than minus 1. Next, if we take object at beyond C, so this one is the object, if we consider this the object, so this object I am taken as B, so that one is placed behind C, right? So the object is placed behind C, then the image is formed between C and F. So here is the here is the B dash. Here is A dash and the point is F. Focus center of curvature is the C, right? So you have to remember, if the object is behind C, If the object is beyond C, then the image is formed at, that is between center of curvature and to the focus, and here also the height of the image is less than to the height of the object and the image is inverted. So here the image formed are real. So here also the image formed is real, and here also the image formed is real because after incident on the concave mirror the rays are converging. At the converging point we get the images are real images. So here also the magnification, if we write the magnification at B dash, it becomes, so M is less than minus 1 because the image is inverted. Okay, this one is the second case. So next, third case is when the object is placed at center of curvature. So this one is the third case. I am going to take this one as D, because here also C we get confused. That's why I am taken the object is placed at C, then the image is also formed at C. So here is the image C dash, right? So here is the magnification, M is less than minus 1, very less than minus 1. Here the height of the object is equal to the height of the image. At the center of curvature, if we place an object, then the image is formed at the center of curvature, and the height of the object is equal to the height of the image. So here also the image formed is real, and also the image is inverted, and here we get the magnification M, that is M is equals to minus 1. So M is equals to minus 1 because the height of the image is equals to the height of the object. So in the numerator and denominator get cancelled, so remaining is minus. That's why the magnification M is equals to minus 1. So this one is the third case. So in the fourth case, I will place the object in between center of curvature and to the focus. That is, here I am going to take E. The object is here, the object B, D, E, all are of the same height. But here the images are, the size of the images are very different. That is, from smaller to bigger. It goes in increasing from smaller to bigger. If we place the object in between center of curvature and to the focus, then the image is formed beyond C. So that is here, right? So the object is placed between center of curvature and to the focus, then the image is formed beyond the center of curvature. Here also the image form is inverted and the image is greater than that of the object, then the magnification M is greater than minus 1. So here also the image form is real and the image is inverted and it is formed beyond C and its magnification is greater than 1. So in the next case, if I place the object at 4, here I am going to take G. So if we place the object at G, then the image is formed at infinity. Image is formed at infinity. That is very greater than minus 1. That is magnification M. Magnification M, that is very greater than minus 1 because the size of the image is very greater than to that of the size of the object, right? Next, and the last case is if I place the object in between, if I place the object in between F and focus, so here is taken as H. So the object is placed between focus and to the pole. So here is the pole. The object between focus and to the pole, then the image form is So here is the image form. So here the image form is virtual and it is erect and it is highly magnified. Here the magnification is, here it is h dash. So here the magnification is, we get m, that is greater than plus 1. So here the image form is virtual and it is erect and it is enlarged. That is height of the object, the height of the image is greater than the height of the object. Right? So this is about the image formation when we place the objects at different positions. So if we remember this one, we can easily answer. For every object, to find the image, we have to draw the minimum 2 rays to draw the image formation. That is, from here we have to take one ray parallel to the principal axis and the second ray which is passing through the focus. After these two rays reflecting, then these two rays are meet at one point, that is this, at this point, then only we can say that the image is formed at C, right? So for short answers, that is for 1 mark, we can't able to draw that all. That's why we have to remember like this. So if you remember like this, then we can easily say that where if we place the object where, that is beyond C or in between C and F or at the F, likewise then we can directly say that the image is real. So from here to here the images formed are real, inverted, real and inverted. So here the size varies. At center of curvature, the size of the, that is size of the object, that is equals to the size of the images. So these are the 6 cases. So you have to remember. So we can apply the same procedure for the lenses also. Okay. So this is the complete of the chapter ray optics. So you have to practice the derivations and also you have to solve the problems based on the derivations. If there are any doubts, then ask me in the group, then I will answer for that your doubts. Thank you.